CS12-Coin-Flip-Game. This is a Jupyter Notebook coin-flip game by Abuzer Yaker Yilmaz that I have placed on Google Colab. This describes a game using the probability of flipping two biased coins. Probabilistic bits. We start with a short introduction to the probabilistic bits to trace the details of the game below. Suppose that we have a biased coin landing on heads with probability 30%, and it is tossed once, but we do not see the outcome. Even though it lands on either heads or tails, our information about the outcome is probabilistic. It is heads with probability 30% and tails with probability 70%. If we consider this coin as a system with two states, heads and tails respectively, states 0 and 1, then we can say that after one iteration, it is in state 0 and 1 with probabilities 30% and 70% respectively. In general, a probabilistic bit is in states 0 and 1 with probabilities p and 1 minus p, where p is a number between 0 and 1. Remark that if p equals 1 or p equals 0, then the bit becomes deterministic. If the above biased coin is tossed once more, the probabilities of getting heads and tails or being in the states 0 and 1 will still be the same. In the following game, by using two biased coins, we will be able to have different probabilities for the states 0 and 1. This game is our first step to determine a probabilistic operator for probabilistic bits. The game. Our friend Asia has €1 and 1 cent. Both coins are biased, and the probabilities of getting heads and tails are as follows. €1, heads, with a probability 60% and tails with a probability 40%. 1 penny, cent, a heads with probability 30% and tails with a probability 70%. Asia flips her coins based on the following protocol. She starts with flipping €1. We should fix an initial condition, otherwise Asia cannot pick any of the coins at the beginning of the game. Whenever she gets heads after flipping, she flips €1 in the next round, and whenever she gets tails, she flips 1 penny, 1 cent in the next round. By using a single bit, we summarize all of the transactions of this game as follows. What these tables are saying is that if the previous state was heads, then the euro will be flipped again, and it has a probability of 60% heads to 40% tails. But if Asia gets a tails, she will flip the penny, the cent, and it has a probability of 30% heads to 70% tails. Thus, every time a coin comes up heads, the euro is flipped. But if tails comes up, the penny, the cent, gets flipped. Task 1. Convince yourself. Convince yourself about the correctness of transitions given in the table. Notice that there is no difference between getting heads from the €1 coin or from the 1 cent coin. Therefore, one bit is enough to represent all transitions. Tracing Asia's 3 coin tosses. Suppose that Asia secretly tosses her coins based on the defined protocol. By using Python, we can calculate the probabilities of Asia seeing heads and tails after 3 coin tosses. Notice, in the previous tasks of coin flipping, we know the ideal ratios, and we experiment many coin tosses and then expect to observe the results close to the ideal ratios. Here we calculate the exact probabilities, the ideal ratio, by using Python. We will not do the experiments as in the previous tasks. We present our solution step by step. First, we initialize the values of the variables probability of head and probability of tail to 1 and 0 respectively to make sure we are flipping the euro to start. Then the first coin flip, the new probability of head, is calculated by using the first row of the table, where the new probability of getting a heads is the probability of getting a head from the previous flip, which we initialized at 100%, now times 60%, as per the first row of the table. To this, we add the probability of getting a tails, which we had initialized at 0%, now times 30%, which we got from the first row of the table, the sum of which becomes our new probability, as stated previously. In a similar fashion, we calculate the new probability of getting tails. We flip the coin again for the second flip, and then the third flip using the same code. Then we print our results. This example does not use random, so each time we run the code, our result is the same. The result is fixed. Task 2, tracing 10 biased coin tosses. By using Python, let's calculate the probabilities of Asia seeing heads and tails after 10 coin tosses instead of only 3 coin tosses. As you can see in the table below, the probabilities remain the same. For this task, Abuzer recommends we use a loop. Let's peek at his solution. Task 2 solution. We copy and paste the previous code where we started in the deterministic state with the probability of heads equal to 100% and the probability of tails equal to 0% as before. We also copied the calculations for the new probability of heads and tails, as well as the update and the output sections. To this code, we add a loop, starting with a range of 10 iterations so that we do not have to cut and paste the calculations and updates repeatedly. These are contained in the indented code block, starting with for I in range number of iterations. Finally, we print our output. This output is exact, as we are not using any random function to arrive at it. If I click here and run it again, my answer remains the same. Task 3. Repeat Task 2 for 20, 30, and 50 coin tosses. Let's look at the solution. First, define the variable iterations as a list of 20, 30, and 50 inside of brackets. Then we make a for loop of iteration in iterations, and each time it loops, set the initial probabilities to 100% for heads and 0% for tails, as we did before. For each iteration, we will print the number of iterations is and the iteration value of 20, 30, and then 50. Then another for loop, where from I to the range of iteration, remember this is 20, 30, or 50, we calculate the new probability of getting a heads or tails result after that number of coin tosses. Here we have it, the number of iterations. And these numbers, again, are fixed. They are totally calculated. Task 4. Repeat Task 2 for 20, 30, and 50 coin tosses by picking different initial conditions. For example, by changing the initial values of heads and or tails to 1/2 each, or reversing the initial values of heads or tails. To begin the solution, again we set our list as a variable named iterations with values 20, 30, and 50 as before, but now we introduce new initial probabilities, and these become the counters for another outer loop for the calculations we did in the previous task. After choosing an initial probability pair, we run sets of 20, 30, and 50 iterations as before, and print the calculated probabilities for each probability pair. Note that we indent each for loop as we go. So our output starts with probabilities of heads and tails both equal to 50%. we see that as we increase the number of iterations, the probabilities begin to converge to the same values as seen between 30 and 50 iterations. Next, when the initial probabilities of heads and tails are reversed to 0 and 1 respectively, something interesting happens. We do not simply reverse the probabilities of getting a heads after 30 and 50 iterations from task 3, but new values.